Hey everybody, welcome back to chemistry. So we're continuing on trying to write out electron configurations of atoms. So now what we're going to do is to try that out for atoms in the form of ions. So I want to teach you how to write out an electron configuration for an anion. Then we'll also do it for a cation. And the final thing I'll talk about is what isoelectronic atoms are. Okay, so the first thing is I want to sort of show you how to write out electron configurations for anions. And anions are actually pretty easy. So you might remember what an anion is. It is an atom with more electrons than normal. So if that's the case, it has more electrons than protons and therefore will have a negative charge. And so to write out an electron configuration of an anion, all you have to do is add extra electrons into the configuration, and they're going to go pretty much as you would expect them to go, and that we use the same rules for writing out electron configurations of anions that we do for regular atoms, in the sense that we always put the extra electrons in the anion into the lowest energy orbital that's available to them, and we just sort of use the rules of putting electrons into higher energy orbitals that we learned before. So let's go ahead and look at some examples here. So here I have an electron configuration of sulfur, and you can see it's an abbreviated form because what I've done is I wrote in the symbol for neon to indicate that sulfur has neon's electron configuration of 10 electrons. Neon is, you might remember, 1s2, 2s2, 2p6. And then in addition to that, it looks like it has other electrons. It has 2 in the 3s and 4 in the 3p. So that is the configuration of sulfur. But how about the configuration for the sulfur anion? This would be sulfur -2, so we have to put in those 2 extra electrons into the configuration. They pretty much go where we would expect them. So what you can see in sulfur's configuration, we have 4 electrons in the p sublevel. With the sulfur anion with 2 extra electrons, we can put those 2 extra electrons into the p sublevel. So now we have filled up the p sublevel with 6 electrons. And so as you might imagine here, because the p sublevel is full and also the s sublevel is full for the third energy level, we've actually completely filled up the entire third energy level with sulfide's electron configuration. So we can write this in another way. If we wanted to, we could just indicate that S2 minus sulfide anion basically there has argon's configuration. So you could also write brackets with the symbol argon, and that would be the same thing. So one thing I'm just kind of pointing out here, a lot of times when you write electron configurations for anions, what will happen is you'll add in extra electrons, and you will find is that they will fill up sublevels and energy levels. And if they happen to do that, then they will have achieved a noble gas configuration, which makes them unusually stable. Okay, so now what I want to do is do a few more difficult ones. And so I want to write out a configuration for the phosphide anion, which is P3 minus, and then I want to do the iodide anion, which is I minus. But just to make as a sort of a useful comparison, let's write out the electron configuration for phosphorus first, then we'll do the phosphide anion. So what I want to do is I want to write out an abbreviated configuration for phosphorus first. So I'm going to flip over here to a periodic table, and I'm going to write on it so we can sort of figure out how to write the abbreviated configuration for phosphorus, then I'll do the phosphide anion. So I'm going to work over here now for a few moments. So the first thing I want to do is figure out where phosphorus is in the periodic table and figure out how many electrons it has. And so it looks like here is phosphorus and it has 15 electrons. And so what I want to do is write an abbreviated electron configuration for phosphorus. And so first thing I have to do is identify the noble gas that just precedes it in terms of electron number. So phosphorus has 15 electrons, and the noble gas that just precedes it has 10 electrons, and that is neon. We can sort of see now that phosphorus is going to have neon's configuration of 10 electrons, and then you're going to add in 5 more electrons for a total of 15 electrons. And so what we might expect is phosphorus with 15 electrons, its configuration is going to look like this. It's going to be neon, And then what we may have to do is we have to figure out the orbitals that the 5 extra electrons go into. So that's a little tricky, so I need to show you how to do that. So one thing you sort of have to be aware of is that you can divide the periodic table into sub-level blocks. And so let me identify 2 of the major ones here. So we have one here, all elements in blue are said to be in the S sublevel block, and that will also include helium here. And then the other one I kind of want to point out right now is here all elements in green are in the P sublevel block. So now let me talk about what that means. If you find an element in the S sublevel block, what that indicates is that the last electron you add to its configuration will go into a S sublevel. So let me give you a quick example of that. So let's take a look at hydrogen. And so you know hydrogen, its electron configuration is this. It has only 1 electron. So there it is, that's 1 electron of hydrogen there. So that is the last electron of hydrogen. So what sublevel is it going into? Well, you know that it's an S sublevel in the first energy level. So we would expect that hydrogen would be a part of the S sublevel block, and it is. Okay, let's say you had helium. Helium has 2 electrons, and you know its last electron also goes into an S sublevel. It happens to be in the first energy level, and so we would expect helium to be a part of the S sublevel block, and it is. Now, let's say we were going to look at lithium here. So here's lithium. It has 3 electrons, 2 are there. So the last electron goes to the next orbital out. So there it is. And so you might remember the next orbital that is filled is an S sublevel, but it happens to be in the second energy level. And so what you might expect for beryllium, beryllium is also going to be in the S sublevel block because its last electron is going into an S sublevel, which happens to be in the second energy level. But now let's think about boron. Is boron going to be in the S sublevel block? Well, here is boron's configuration. It has 5 electrons. There are 4 here. And so the 5th electron, you know, is actually going to be put into a p orbital in the p sublevel in the second energy level. So the electron goes here. So with these elements here in green, what you would expect is that the last electron you place in its configuration will go into some kind of p sublevel. Now additionally, one other thing you have to sort of understand is what energy level that electron will be in. So let's consider the S sublevel block. So the energy level that that last electron will be in the S sublevel block is easy to figure out. It has the same value as the period of the element. So for example, hydrogen and helium are in the first period, therefore their last electrons will go into the first energy level. Lithium, beryllium are in period 2, and so the last electron added to its configuration will go into the second energy level, and so on. And so for example, if you were down to cesium, what you would find is that it has 55 electrons, and what you would see is that that last 55th electron of cesium would be going into an S sublevel, but it's going to be in the 6th energy level. Okay, now how about elements in the p block? Same deal here. This row of elements are in period 2. And so therefore that last electron for these elements here will be going into a p orbital that's in the second energy level, and so on. So for example, if you're like looking at, say, polonium here, its last electron will be going into a p sublevel because polonium is in the p block, and it's going to be into the 6th energy level. Okay. So at this point, let's go ahead and try again and see if we can figure out the electron configuration of phosphorus. Okay, so here we go. So let me erase some things here really quickly. Clean this up a little bit. Okay, so here is phosphorus. And it has 15 electrons. So we're going to write an abbreviated configuration. And so you can see that the noble gas just preceding it is going to be neon. And so next thing you have to do is figure out the next orbitals that the additional 5 electrons go into. So 2 of the 5 electrons you're going to add in will next go into the s sublevel in the third energy level. We know that because we're passing through the s block. Now, once we're out of the s block, we go across the periodic table and we're now into the p block in the third energy level, and we're going to add 3 electrons there. And so here the configuration is going to be 3p3. And so this is phosphorus's electron configuration. Now, can you figure out what the phosphide anion's configuration would be? Phosphide anion is p3-. There are 18 electrons. And so where will additional 3 electrons go? Well, they will go into the lowest energy orbitals that are available to it. So you're like, oh, is this a 6s orbital or a 5p orbital or a 10d orbital? What is it? Well, if you look carefully at the phosphorus's atoms configuration, what you can see is that there are only 3 electrons in the p sublevel. The p sublevel can accept up to 6 electrons, so we can put 3 more here in the p sublevel in the third energy level. So the phosphide anions should have this configuration, neon's configuration, and then 3s2, 3p6. Okay, so also there are some other sublevel blocks you need to be aware of. So these elements in red here are part of the D sublevel block, and so what you can imagine this means is that if you pick one of these elements here in the block, when you're writing out its configuration, its last electron will go into a D sublevel of some energy level. Now, if the element happens to be in the first row of the D sublevel block, something like iron or nickel, something like that, you need to know what energy level that electron is going into. And it turns out that here, this first row here of the D sublevel block, the energy level that the D sublevel is in is the third energy level. Now, if you have an element in the second row of the D sublevel, then the electron in the D sublevel will be in the fourth energy level, and so on. Also, just be aware that there is an F sublevel block here. Here is the F sublevel block. And you just have to remember that the elements in the first row of the F sublevel block, their last electron in their configuration will be going into an F sublevel. If the element is in the first row, it'll be an F sublevel in the fourth energy level. If it is an element in the second row, it's going to be an F sublevel in the fifth energy level. Okay, so using that information, let's go ahead and figure out the configuration of the iodine atom. So we have iodine, it has 53 electrons. What is its electron configuration? We want to do an abbreviated one. So first, let's figure out where iodine is in the periodic table. It is here. And so we identified the noble gas that just precedes it. It is krypton with 36 electrons. So we write krypton like this. And we know that that has 36 electrons. And so we need to add more electrons to get up to a total of 53 electrons. And so we go from krypton, and you can see as we fill up to head over to iodine, the first thing we go through is the S sublevel block. So we can see that 2 electrons are going to be added to an S sublevel. The problem is, what energy level is it in? So 1, 2, 3, 4, 5. It looks like it's in the 5th energy level. So the next 2 electrons are in 5s2. And then to get closer to the iodine atom, we're going to have to go across the D block. And so you have to recall whether these D orbitals here that are being filled, is it in the 3rd, 4th, 5th energy level? What is it? Well, if the element was in the first row of the D block, it would be the 3rd energy level. Because we are going across the second row here, it's going to be in the 4th energy level. So the 4D will be filled up with 10 electrons. And then finally, it looks like we need to add 5 electrons to the next orbitals. And so now we're in the P block. Let's see how far we are down here. 1, 2, 3, 4, 5. It looks like the P block that is being filled here is in the 5th energy level, so we write 5p5. If we have the iodine ion, it has 54 electrons. And so what would its configuration be? So basically, you sort of know now that if it's an anion, what we do is we add the electron to the lowest energy orbital that is available to it. And so that looks like it's going to be a 5p orbital. And the reason is that when we have the iodine atom with 53 electrons, we only put 5 electrons into the p sublevel that can accept 6. With the iodine ion with 54 electrons, that we're going to add one more. And so the p sublevel has room for one more. And so we're going to make this 5p6. And that should be the correct configuration for the iodine ion. One more thing to point out. One of the things you might notice is that with the iodine ion here, you will see that the 5th energy level is completely full. And so we are now at a new noble gas configuration. So another way you can write out the configuration of the iodine ion is like this. We are now at xenon's configuration, and so the iodine ion is xenon's electron configuration, so we can also write that for the iodine ion. Okay, so now let's look at the electron configuration for cations. Okay, so if you're trying to figure out the electron configurations for cations, it's a little bit different than what you would expect. You don't necessarily pull out electrons in the reverse order that you put them in. That's what you might expect for cations. Instead, this is what you do. Is if you have some kind of element and you want to find out the configuration for the cation, what you do is you remove electrons from the numerically highest energy level first before you might dip into a D sublevel. That's the general rule. So if you have electrons filling up, for example, a S and a P sublevel without a D sublevel, to form the cation, you pull out electrons from the P sublevel and then the S sublevel next to maybe form the configuration of the cation. Now, if you have a transition element, you do the same thing, but make sure you pull the electrons out of the highest numerically energy level from usually an S sublevel before you pull them out from the D sublevel. So let me just go through a few quick examples. So there I have an electron configuration for barium. It is an abbreviated configuration, so I show the configuration or symbolize xenon's configuration there, which has 54 electrons. And then barium has 2 more electrons than that, so we write xenon's configuration and then we write 6s2. So what would be the configuration for barium 2+? It's pretty easy, right? So again, you remove electrons from the numerically the highest energy level sublevel. So the highest energy level sublevel is the 6th energy level. You remove those 2 electrons from the 6s. And so barium 2+ should be just xenon's configuration without 6s2. How about something like indium? There is indium atoms electron configuration. That is not an ion there. That's the indium atoms configuration. And what you can see, it has krypton's configuration with 5s2, 4d10, and 5p1. So if we wanted to write out the configuration for indium 2+, what do we do? So here what you do is, because the p sublevel of indium was the sublevel that was filled in last with electrons, we remove electrons from that first before we remove from the S sublevel. Importantly, we remove the electrons from the P and S sublevel, which is in the higher numerically energy level, before we remove them from a D sublevel. So if you want to write a configuration for indium 2+, what you have to do is remove that 1 electron from the 5p sublevel of indium, and that will be gone. But then you don't go into the 4d sublevel yet. Before you do that, you remove an electron from the 5s sublevel, because that is numerically the highest energy level. And so indium 2+ should be krypton's configuration. There's 1 electron left in 5s, and then all of indium's 4d10 electrons are there. Now, if you have the indium 3+ ion, there you will remove from, starting with indium, the 1 electron in the p sublevel and both electrons in the s sublevel. So once those 3 electrons are gone, what you're left with, you don't have to write down 5s0 or 5p0. You can just write what you have left, which is krypton's configuration with 4d10. Okay, so let's try some more difficult ones. And so what I'm going to do is I want to write out abbreviated configurations for these atoms and then write out configurations for the ions. So let me just go ahead and do that on the board right now. Okay, so what is the electron configuration of calcium? So calcium has 20 electrons. And so I'm hoping maybe you'll to do this on your own, but if you look carefully at a periodic table, what you'll see is that the noble gas that just precedes calcium is argon, and it has 18 electrons. So when we write argon's configuration there, we have written out 18 electrons. So we have 2 more to go. Excuse me. So if you look carefully as to what orbitals appear after argon's configuration, what you'll see is going to be a 4s orbital. So that will be 2 electrons. Okay. Now, if you have calcium 2+, you're down to 18 electrons. And so what you're going to do is you're just going to remove the highest energy level electrons here, and so it'll be just argon. Numerically, the highest energy level electrons go first, and so you're just left with argon. Okay, now how about the next one? We're going to do the configuration for the stannic ion first, but first let us figure out what the configuration of the unionized form of that ion is, which is tin, which is Sn. So tin has 54 electrons. Okay. And so its configuration is krypton, because that is the noble gas that just precedes it. And then what I think, as I recall, you have 5s2, 4d10, and then you have 5p2. And so that should be the correct configuration for the unionized tin ion. But let's say we're removing 4 electrons to produce the Sn4+ ion, the stannic anion. So it's Sn4+. This will have 50 electrons. And so you would have to remove 4 electrons from this neutral atoms configuration. So which 4 do you remove? Again, you refer to the rule that you remove electrons from the numerically highest energy level, the S and the P sublevels first, before you dip into a D sublevel. And so here we have some electrons in the P sublevel. We pull those out first before the S. We can pull out 2 electrons from this P sublevel, and then 2 more from the S sublevel. And then we did not have to dip into the D sublevel to remove a total of 4 electrons. And so here the configuration of the stannic ion, Sn4+, this will be 2 electrons gone from 5p2, so that would be 5p0, 2 electrons removed from 5s2, so that is 5s0. You don't have to write that out. We didn't go into the D sublevel of the 4th energy level, so there are all 10 electrons there. So that should be the configuration of the stannic ion. Okay, so we're going to move on. So how about trying to figure out the electron configurations of cations that are in the transition metals? In other words, there may be some point in time where you have to find configurations and you're actually having to pull electrons at some point from the D sublevel. So let me show you how to do that. So basically the same rule applies in that what you do is if you are trying to find the configuration of a cation in the transition metals, you pull off electrons from numerically the highest energy level first, and usually that is an S sublevel, before you start pulling an electron from the D sublevels. And so I think the best way for me to explain this, beyond these examples I have on the screen, is to sort of do this on the light board. So I'm going to work here. Okay. So let's say you have vanadium, and vanadium has 23 electrons. So can you write out an abbreviated electron configuration for vanadium? And so the noble gas that just precedes vanadium, you can look it up, should be argon with 18 electrons. So I'm going to write argon here. and that covers 18 electrons. And then we have to put in 5 more. So we would have 2 go into the 4s2 sublevel. And then you might remember after the 4s2 is filled, then you start going into the 3d orbitals. And so we have 3d3. So that should be vanadium's configuration. Okay, now, what's the configuration for vanadium ion, which is 2+? Now we're down to 21 electrons. So what would be that configuration? So what you're going to have to do is take the vanadium atom's configuration and remove 2 electrons from its configuration to give you the correct configuration for vanadium ion. The question is, which 2 electrons do you remove? Do you remove them from the 3d sublevel, or do you remove them from the 4s sublevel? And again, the rule for cations applies in that you remove electrons from the numerically highest energy level first before you start dipping into a d sublevel. So numerically, the highest energy level that we have here is the 4th energy level. So we pull out those 2 electrons for the 4s sublevel first. So we only need 2 electrons to remove to get the vanadium ion. And so it should be argon. And then I'm going to pull out these electrons here. And so this would be 4s0, which you don't have to write. And so you could just write 3d3. Now, let's say you have vanadium 3+ ion. So this is 20 electrons. Okay, and so what would its configuration be? Where would you remove an electron, 1 more electron? Now you can go into the d sublevel. So we've pulled out the electrons from the 4s. There's no more electrons in the 4s. We can now go into the d sublevel. It should be argon 3d2. Okay, so let's do the next one, a little bit trickier. Okay, so let's say you have copper, which has 29 electrons. We'll figure out what the configuration for the copper 1+ ion and the copper 2+ ion is in a minute. But first, let's figure out the configuration for the copper atom. So again, the noble gas that just precedes copper is argon again. And so that takes up 18 electrons. So the 19th and 20th electron go into the 4s sublevel, so it's going to be 4s2, or at least that's what you would think, right? Now, we have 9 more electrons, and you would think it would be just 4s2, 3d9. Now, I'm kind of hoping what you see is that I made a mistake. And so what we now know from a previous discussion is that when you have a situation where you have electrons filling up the d sublevel and you're just 1 away from a completely full d sublevel with 10 electrons, what will happen is the atom will lose one of its 4s electrons, and then that electron will go to completely fill up the d sublevel with 10 electrons. So this is really not copper's correct configuration. Its correct configuration is where one of the electrons has left the 4s sublevel, and now we're down to 1 here, and it's gone to join the other 9 electrons in the d sublevel, so it should be 3d10. So that is copper's correct configuration. Now, can you write out the configuration for copper with 28 electrons? So now we're going to take copper's configuration and we're going to lose 1 electron, but the question is, do we lose an electron from the 4s sublevel or the 3d sublevel? And so the same rule applies. Pull out electrons from numerically the highest sublevel first, which is the 4th one, before you start dipping into the d sublevel. So here with copper plus here with 28 electrons, we're going to remove an electron from the 4s sublevel, so it'll be 4s0, which I'm not going to write, so it's going to be 3d10. How about copper 2+? So copper 2+, now we're down to 27 electrons, and so if we have to remove 1 more electron, now we really have no choice but to go into the d sublevel. And so here we would say this is 3d9. Okay, so let us move on. There's one more thing I want to talk about, and then we're done. So what you need to understand is what isoelectronic atoms are. And isoelectronic atoms are are atoms that may be different in their chemistry, they may be completely different elements, yet they have exactly the same electron configuration. So let me give you some examples of that. Okay, so what I want to do is write out some atoms or ion structures that are said to be isoelectronic with argon's electron configuration. So let me write out argon's electron configuration really quick. So argon has 18 electrons. And so if you wanted to, you can write out the configuration the long way, which I'm going to do, which is going to be 1s2, 2s2, 2p6, 3s2, 3p6. And now what I want to also do is write out an orbital notation for this. So it's 1s, 2s, 3 2p orbitals, a 3s, and a 3p orbital. Okay? And so what you would find, because argon has 18 electrons, is that all of these orbitals I wrote out will be filled up with a pair of electrons, and that should give us a total of 18. Okay, so the question is, can we write out some configurations for other elements that may be ionized? Other elements like, say, chlorine, or sulfur, or for example, calcium, other elements that are ionized in such a way that they have the same electron configuration as argon? And the answer is yes. So let me show you how you could do this. So let's say you have chlorine. And so you know that chlorine has 17 electrons. You can look that up. And so you could write out chlorine's orbital notation like this. So what we have here for chlorine is basically, it looks similar to argon's notation, but there's one less electron. So the first question I have to ask you is this: is chlorine's electron configuration here with 17 electrons isoelectronic, meaning does it have the same configuration as argon's with 18 electrons? And the answer is no. And the reason is you can see with argon, there are 6 electrons in the p sublevel. With chlorine, there are only 5. So these two atoms are not isoelectronic. But how about this question? If we add an electron to chlorine, making it the chloride ion, is that configuration isoelectronic with argon? Well, let's check. So we have the chloride ion here, and so I'm just going to add another electron to the count, so now we're up to 18. So you know the rules for writing electron configurations for anions. You just put electrons that appear, they go into the lowest energy orbital that's available to them. So we add an electron here. It goes into the p sublevel. This is now the chloride ion. So the question is this: does chloride ion's electron configuration, is it the same as argon's? And the answer is yes, it's exactly the same. So we would say that argon and the chloride ion are isoelectronic atoms. Okay, let's do one more. Let's say we have calcium. So we have calcium, and it has, let's see, calcium has 20 electrons. So its configuration is 1s, 2s. Okay, so my first question to you is this: is the calcium atom's electron configuration isoelectronic with that argon's or the chloride ion? And I think you can see the answer is no. And the reason is because now calcium has a different configuration, right? Now we have 2 more electrons that go into the 4s sublevel. So this is not isoelectronic with argon. But can we easily make a change somehow to this configuration so it is isoelectronic with argons? And the answer is yes. It's really simple, right? All we have to do is take this configuration for calcium and then have calcium lose 2 electrons. So let's just turn it into 2 plus. So now we're down to 18 electrons here. And so if you lose 2 electrons, those electrons will be removed from the numerically highest energy available that is there. So you can see the numerically highest energy level is the 4th energy level. We don't have any electrons in P, so we can't remove those, but we have 2 electrons in S. We can remove those. So in the calcium ion, this is calcium ion's electron configuration. If you wanted to, you can just remove this. And so what you can see, the calcium 2+ ion has an electron configuration that is isoelectronic with chloride ions and argons. Okay, so let me do one more question, which is a really good one. So we're trying to figure out, are the following atoms with 27 electrons isoelectronic? Copper 2+ and cobalt. Okay, so the point I kind of want to make here with this problem is just because you have 2 atoms with the same number of electrons does not mean that they are isoelectronic. Not only would they have to have the same number of electrons, but they need to be disposed in exactly the same way in the orbitals. If they're disposed in the same way in the orbitals, then they're isoelectronic. So let's compare cobalt to copper. Both have 27 electrons. So we have cobalt here with 27 electrons, and then we have the copper ion with 27 electrons. Okay, so what is cobalt's electron configuration? I'll write an abbreviated one. So we have argon's configuration with 18 electrons. And so we now need to put in 9 more. So it's going to be 4s2, and so it's going to be 3d7, right? So let me write out an orbital notation for this. So it's just to confirm, it's 4s, and then there's 3d, 1, 2, 3, 4, 5. So there's 4s2 here, 3d7, 1, 2, 3, 4, 5, 6, 7. So that's cobalt's electron configuration. But how about the copper ion? What would that be? So copper ion, first, let me write out what copper's electron configuration is, and then we'll figure out the copper ion. So let me digress just a second here. I'll write copper's electron configuration. So copper at 29 electrons, so this is going to be argon. And what you might remember, it has a weird configuration. It is 4s1, 3d10. So remember why that is? It's because you have 4s and then 3d10, 5 3d orbitals. And so what will happen is that copper will pull off one of its 2 electrons in 4s such that it can completely fill up the 3d sublevel of 10 electrons. So this is the copper atoms configuration. But how about the copper 2+ ion? So the copper 2+ ion is 27 electrons here. What would its configuration be? So you have to remember with the copper ion, where are you removing electrons from to get 2+? So what you have to do is first remove electrons from numerically the highest energy level, which is the 4th energy level, before you start dipping into the 3d sublevel. So the copper 2+, its configuration should be argon, and we remove that one electron there from the 4s sublevel, and then we have to remove another one from the 3d sublevel. So it should be 3d9. So the copper 2+ ion should look like this. It should be 1, 2, 3, 4, 5. And this is 3d with 9 electrons. The 4s is empty, so I'm going to leave that out. So this has argon's configuration as well. So now let's compare here cobalt's electron configuration with 27 electrons versus the copper ions with 27 electrons. And what you can see is that although cobalt and the copper ion have the same number of electrons, they have completely different electron configurations. Therefore, cobalt with 27 electrons is not isoelectronic with copper 2+ ion, which also has 27 electrons. Okay, thank you for listening to that presentation. We will see you next time.